Magnetic fields 3. Charged particles in electric and magnetic fields. You need to, it says on the syllabus, be able to compare the deflection of particles, charged particles in electric and magnetic fields. Now, the first diagram I've done is neither of them. Imagine driving a car off a cliff, and what's going to happen is that horizontally, ignoring air resistance, horizontally it'll go at a constant velocity, vertically it will accelerate due to gravity, and the result will be that the car will do a path called a parabola. Its path will be parabolic. The diagram top right is if something like a proton enters an electric field, well, the same thing is going to happen. Horizontally, it will travel at a constant velocity, and then in the direction of the field, it will accelerate, and you'll end up with a parabolic path. So that is the path of a moving charge in an electric field. The path of a moving charge in a magnetic field is different. It's not parabolic, it's circular. And why is it circular? Because the direction of the force is constantly changing. The direction of the force acting on the particle in a magnetic field will be centripetal, because it will always be at right angles to its velocity. Another big difference is that the particle doesn't gain kinetic energy. It doesn't speed up. In an electric field, the particle will gain kinetic energy. It will speed up. In a magnetic field, it just changes direction. It's a little bit like the moon in orbit around the Earth. The moon isn't speeding up, it's just changing direction due to the Earth's gravity. Okay? And another big difference is that the charged particle actually has to be moving to experience a force. In an electric field, it doesn't matter whether it's moving or not, there'll be a force. In a magnetic field, the charged particle has to be moving, because then you'll have a current, and the force is acting on the current. Here's an equation you need to know. The force on a moving charge, F equals BQV. If the charge is an electron or a proton, then it becomes F equals BeV. F is Bill or Bev. But in general, F equals BQV. A moving charged particle enters a uniform magnetic field. Now, a very common question is to show that the radius of the path is proportional to the momentum of the particle. And the way you start is with basically F equals ma, and from F equals ma, BQV equals mv squared over r, so BQR equals mv, which is what it asked for. But you should learn that little derivation. It's a very common little question to ask. Particle accelerators. I take my class to Geneva. We go to CERN, where the Large Hadron Collider is. There's Ryan pointing at a mock-up of the LHC. Now, in a particle accelerator, electric fields are used to give the protons kinetic energy. So electric fields actually make the protons go faster. It gives them kinetic energy, well, as much as it can, relativistic effects ignored. Magnetic fields just keep them going in a circle. So the magnetic fields keep your protons moving in a circle, and then every time they go round, electric fields give them more and more and more energy.